We're going to look at one of the most important uses and applications of calculus, which is optimization. And we're going to look at mostly geometric applications of this, so areas and volumes. And yeah, why is optimization so important? Well, we'll see in the context of the examples, but in order to solve these optimization problems, so what we're doing is we're actually finding maximum and minimums. And as we've seen through graphing these functions, that we can find these maximum and minimums by essentially doing things like first derivative, find those critical points, and then you can check if they're a maximum or a minimum. And in general, what do we want to do if we're solving these optimization problems? So we want to make a sketch. That's going to be really helpful because sometimes it's not going to be obvious how we create our equations. And we need an equation to work with, a function to work with, in order to do things like take the derivative. Make sure to define your variables though. So using let statements, make sure to do that to be clear about your solution process. We also need to know what we're actually trying to maximize or minimize. That's going to be the key part of the question because that's what we're going to take the derivative with respect to. And if there's more than two variables, well, then we just need to figure out how can we rewrite the one variable in terms of the other variable. And that's going to come from using your diagram that you've drawn. In some sort of way, you'll be able to do that. Then the last part is we'll actually doing the derivative. Because again, once you set up the equation, the task is a little bit more straightforward. Take the derivative, find the critical point, check if that's the maximum or the minimum. We will also need to check our endpoints though. So you'll see this last part here, check the endpoints based on the domain. But essentially, what's going to happen is you're going to find the critical point. That could be a local maximum or minimum, but the actual ends of the functions, if we're like restricting the domain, might actually be themselves higher or lower than that. So we'll need to be careful that that comes from what we call the extreme value theorem. So, and I just said that, extreme value theorem. So what the extreme value theorem says is that if we're looking on an interval, specifically a closed one between A and B. So we've got some intervals here. The interval itself will for sure have a maximum or a minimum. Not only that, the maximum or minimum will either occur at a critical point. So in the diagrams that we have here, got a critical point there, critical point there. So it'll occur there if it's continuous, or it'll occur at the end. So we have an example here of a interval where it's just going downwards on that interval. So in this case, the maximum is at the starting point. So it's either at the critical point or at the end point. So we're just going to always have to double check that. All right, let's get into some actual examples, see what this is all about. So the first example, just a simple one of where optimization comes into play is we're looking to make a cylindrical tin can. Cans are used all over the place, and we want to maximize the volume of the can given some amount of material. So very simple, but also very, very much important kind of application because if you're going into any sort of manufacturing, we want to be able to maximize things to reduce cost or to be able to maximize what we're selling. So yeah, it's important for those kinds of areas. So let's draw a picture. So we want a cylinder, so let's draw a cylinder. Let's see how good I can draw this cylinder. Okay, so this cylinder is coming together. Ooh, that's a rough circle there at the bottom. And, well, let's give it some variables. So we're going to have a radius r and a height h. Since I'm introducing variables, let's define those variables. So let h be the height of the can. And then let r be the radius of the can. Okay, so we've got that. What are we actually looking to do? So we're looking to use up 500 centimeters squared. So that is a surface area. So let's just define our surface area. So let SA be the surface area of the can. So we have that much tin to work with. And what are we looking to maximize? The volume. So that's going to be our key variable. So that's what we want to create our function. We want to create a function in terms of volume. Well, like we want to make it a volume function. And then we'll see how we can maximize that. Okay, so first of all, we know that the surface area is 500. So all I'm going to do is just say surface area is equals 500 centimeters squared. And well, what's the surface area of a cylinder? So for a surface area of a cylinder, you have the two circles. So pi r squared is the area of a circle, so 2 pi r squared. And then the vertical portion, well, the circle has a circumference of pi r h. Or sorry, the circle has a circumference of 2 pi r. But then you're going up by h, so 2 pi r h. So that's the surface area of a circle, or of a cylinder, I should say. And then, since we're wanting to find volume eventually, to maximize that volume, let's just write the formula for the volume. So for a cylinder, the volume is pi r squared h. Okay, so right now we have an issue. In the volume of the cylinder, we have two variables, r and h. If we want to do things like derivative, we want just one variable. So what we want to do is we want to basically take r or h and isolate for one of them, basically be able to get the one in terms of the other, and we're going to do that using our surface area equation. So what I'm going to say is use surface area to find h in terms of r. You could do it the other way around, but the reason why I'm doing h in terms of r is I'm going to be plugging it into this volume equation. R is squared, h is not, so that'll make that a little bit easier. As well, in this actual equation for surface area, if we look at it, well, in the actual equation, you have 2 pi r squared plus 2 pi r. You just have a single variable h, so it's going to be a lot easier to isolate for h. So theoretically, you could make it work both ways, but isolating for h is definitely the easier way to go here. So if we want to isolate for h, chuck over the 2 pi r squared. And then we're going to be dividing by 2 pi r. We could also divide, well, okay, yeah, let's divide by 2 pi r. I'm just going to switch the sides. Everything is divisible by 2, so let's just reduce things down by 2. And we're going to be doing derivatives, so let's just do the individual division there. So 250 over pi r. That might make things a little simpler. Minus pi r squared over pi r, which would just become r. Okay, so we have our height in terms of our radius. So now let's go ahead and, all right, so let's plug it into our function for volume, and we're going to get pi r squared times 250 over pi r minus r. Okay, a little bit of distribution here, and we're going to get 250 over 250 pi r squared over pi r. We're going to cancel some things out, and that's going to be minus pi r cubed. Pi's are going to cancel. One of the r's is going to cancel, so you get 250r minus pi r cubed. Okay, so now we have the volume in terms of a single variable. We can take the derivative with respect to that single variable. So let's do that. V prime, or I'll call it dv with respect to r, since that's the variable we have there. And that's just going to be 250 minus 3 pi r squared. Okay. And, well, we want to see what the critical point is for the potential maximum. So 0, set that equal to 250 minus 3 pi r squared. And rearranging that, we're going to get 3 pi r squared equal to 250. And I'll just do this in a couple steps. 250 divided by 3 pi, or r, when you take the square root of that, well, you're going to get a positive and a negative answer, but of course, the negative answer won't make sense. So we'll just approximate it and say it's about 5.15 centimeters. Okay. Let's check, is this actually a maximum? So there's two ways you could do this. You could use the second derivative test or the first derivative test. So what I'm going to do is I'm going to simply use the first derivative test. No, second derivative test. Seems like an easy enough derivative to do again. I'm just getting some more space here, and then we'll continue. Okay, so let's do the second derivative. So dv, or d squared dr squared, is just going to be negative 6 pi r. And for the second derivative test, all you need to do is plug in 5.15 into that. And just check the sign. So let's evaluate that at r equal to 5.15. And if you do that, well, in this case, I don't even really need to do the calculation. A negative number times pi times 5. It's definitely going to be less than 0. So therefore, r equal to 5.15 is a maximum. Okay. And what is that maximum volume? That's the actual, if we go back to the question is asking for find the maximum possible volume. So let's plug it in. So volume is going to be pi. Well, we'll do the simplified version, like when we multiply it in, we get 250 r minus pi r cubed. So 250, 5.15 minus pi, 5.15 cubed. And in this case, that'll be approximately, calculating it out, 859.39 centimeters cubed. So there we have it. Therefore, the maximum possible volume is 859.39 centimeters cubed. All right, let's take a look at this next problem. So we have a farmer plans to build a fence in a rectangular field next to a river. And the side of the field along the riverbank does not require fencing. And the two sides of the field that are perpendicular to the river have to have rust-resistant fencing. So that's going to cost $9 per meter. And then the length parallel to the river, well, that's going to cost $7 a meter. And in total, we want the area to be 400 meters squared. So we want to figure out what dimensions will minimize the cost of building the fence, but the width has to be at least 5 meters and no longer than 10 meters. So let's draw this out. So we're going to have the river along here. We're going to have a width there. Only I could draw straight lines. Something like that. Okay, So width, width, and length. So let's, again, always define your variables. So let W be the width of fencing. And let L be the length of fence. Okay. And what are we trying to figure out? We're trying to figure out what the minimum cost is. So let's introduce a variable for the cost. Let C be the cost of the fence. And then, well, what other information are we going to make use of? We have an area. So let's make use of the area. So let A be the area of the field. Okay. So I'm just going to reiterate the fact that the width must be between 5 and 10. So let's just kind of write that down as a domain here. So the width has to be between 5 and 10. So let's go ahead and let's try to come up with some sort of equation for the cost and then make sure that equation is in terms of one variable. Okay, so what is the cost going to be? Well, the cost is basically going to be related to the perimeter. So we need to figure out how much width we're going to use, how much length we're going to have, because that's where the cost is coming from. So we have two widths. So I'm going to have a 2 times a W. How much does the width cost? Well, let's go up here. The width, that's the part that's next to the river, that's going to cost $9 per meter. So all I'm going to do is multiply that total amount of width that we're got in our diagram there and multiply it by 9. And in fact, it might be helpful just to include that on the diagram. So we have width there at $9 per meter. And the length, that's $7 per meter. And so what we're going to do for the length here, there's only one length. We don't need the river to have a fence on it. So just one length times 7. Let's just neaten that up a little bit. So it's going to be 18W plus 7L. 18 times the width plus 7 times the length. Okay, but what other information do we have? We also have information about the area. We want the area to equal 400 meters squared. And we know that, well, it's just a rectangle. The area of a rectangle is just length times width. So we know that in the end, 400 must equal length times width. So this is a situation where we want to get the cost function in terms of one variable. And it doesn't matter which variable you get it in terms of, whether it's the width or the length, you can choose either one. So what I'll do is, let's just isolate for the width. Say it's 400 over L. If you isolate for the length, that'd be totally fine too. And let's sub in width equal to 400L, or 400 over L, in C. All right, and so now our cost is just going to be 18 times 400 over L plus 7 times L. Here we have an equation now in terms of cost, in terms of a single variable. So we can go ahead, basically neaten up the way this equation looks like. So, well, 18 times 400 is just 7,200. And that's over L plus 7L. And then what do we want to do? Well, we want to minimize this cost. So this cost function is what we've built up. So we need to find the critical points, find out where on this cost function the minimum is. So we'll do prime notation now. So C prime, and in fact, since it's in terms of a single variable, we can say C prime of L. So C prime of L is just going to be, well, the dividing by L, that's the same as -1 for your exponent. So it's just going to be negative 7,200 over L squared plus 7. Okay. And to find the critical points, set that equal to 0. Okay, and now it's just a matter of rearranging this and just carefully solving this out. So we're going to get -7 equals -7,200. Eventually those two negatives will cancel out, so we'll get some positive number, which is what we want. We'll have, I'll flip the -7 in the L squared. So -7,200 over -7. Or you could just think of it as positive because you have two negatives. And so taking the square root of that, that's just going to be our answer. So we'll move this up here. But yeah, so 7,200 divided by 7, that square rooted will be approximately 32.07. Okay. Well, let's just double check what the width is in this case. So the width is just going to be 400 divided by that. Let's include our units. 400 divided by 32.07, and that is just 12.47. All right, feels like we're done, right? Well, we need to be careful, because what did we say about our domain? Well, 12.47, this is actually outside our domain. Because our domain was from 5 to 10. So that means we have no critical points in the domain. But that doesn't mean there's no maximum or minimum. There is still going to be a cheapest option. What it does mean, though, is that the cheapest option is going to be one of those endpoints. So we need to check our ends. So check endpoints. So essentially check what's the cost if you use $5 or a width of 5 meters, I should say. And then what's the cost if you use a width of 10 meters, because those are the endpoints. So W equals 5 meters. And then that's going to mean the length is equal to 400 over 5, which is equal to 80 meters. And then the cost associated with that is just going to be 18 times 5 plus 7 times 80. Just using our function that we developed before, and that would be $650. Okay, and do the same thing with 10 meters. Let's find out the associated length. I don't know why I'm using capital all of a sudden. Let's change that. And then 400 divided by 10, well, that's just going to be 40. And so then the cost is just going to be 18 times 10 plus 7 times 40. And that is just actually $460. So that's definitely the cheaper option. So therefore, a width of 10 meters and length 40 meters minimizes cost. Okay, so that's a look at another optimization problem. Let's look at one final one, which is the area of the largest rectangle that can be inscribed in a right triangle with less legs adjacent to the right triangle of lengths 5 and 12. Okay, that sounds like a handful there when you first write it down or read it. Let's just draw a picture though. So we have a rectangle inside a right angle triangle. So let's draw the right angle triangle. And then, here, I'll try this again. Draw the right angle triangle. Draw it across like this. And then draw that. It's maybe not to scale, but we will try our best here. So let's say we have a bottom length 5, side length there of 12. So we've got that. And we want to put a rectangle in here. So let's just draw a rectangle in here. We want to try to get the biggest rectangle in here. Who knows what that'll exactly look like? Okay, sorry, I just want to make this as nice and straight as possible, apparently. There we go. So that's our rectangle. And, well, what do we have in a rectangle? We usually have two lengths, or two measurements that we care about, the length and the width. And let's define those then. So let L be the length of the rectangle, and let W be the width. Okay, so we've got our variables defined. Well, what else do we need? We want to figure out the area of this rectangle, so let's define that. Let A be the area of the rectangle. Okay, so now where are we going to go from here? Well, I've labeled the rectangle L and W. Let's finish off the diagram. So we have this portion on the top. Well, the bottom part's L, and we know the whole thing is 12. The top must be 12 minus L. And same thing with the bottom. If we have one portion W and it's 5 in total, must be 5 minus W. And that's going to come in handy. The other thing we want to make use of, well, we're actually going to make use of similar triangles here. So let's see how we're going to make use of similar triangles. So first of all, we have this triangle in this top portion. Let's call that triangle 1. Well, looking at that triangle and actually the whole big right angle triangle that we have, I'm just highlighting that, the entire triangle. Oh, did not want to erase that much. Let's do that instead. We'll call that triangle 2. So basically, 1 and 2 are similar triangles. Okay, and how are we going to use that? Well, what matters about similar triangles is that the ratios of the sides in the similar triangles, those ratios are the same. That's kind of actually what all of trig is built upon, is the ratios of triangles being the same. And so that's similar triangles. So how are we going to make use of that? So let's take a look at our triangle 1. So as you can see, I just quickly labeled the top of the triangle there, W. So we have, let's first use the left side. This left side, 12 minus W, or 12 minus L. The corresponding side in the big triangle is just the length L. That is a ratio there, 12 minus L to 12. That ratio is going to be the same as the ratio of the bottom length. So the bottom starts with W, this portion here, and that's going to be the same as the entire bottom of the big triangle. And well, what's the entire bottom of the big triangle? 5. So we've got a ratio, and from there we can actually basically solve for the one in terms of the other. So I could get what is W in terms of L. And quickly rearranging that, I'll just move the 5 over. Just 5 times 12, so I'll just do this in 2 steps. Let's just multiply the 5 in. So it's just going to be 60 minus 5L over 12. So there we have it. We actually have a way of measuring out the width in terms of the length. And again, why are we doing this? Well, in the end, we always want to get our measurements down to one variable. And if we take a look at the area, well, what's the area of the rectangle? Length times width. We have 2 variables there, so we want to replace, so sub in W with what we just found out. And so now we can say that the area is actually length times this new measurement that we just found. And let's expand it out. It's always nice to have things expanded out. So we're going to have the area is just 60L minus 5L squared over 12. Okay, so we've got our area in terms of one variable. Again, we always want to get things in terms of one variable. So now we can take the derivative with respect to L, since it's just a single variable. And the division part doesn't matter. It's just dividing by a constant. So you can think of dividing by a constant like a coefficient in front. It's just going to stay as over 12. So really what matters now is the numerator. 60 times L is just derivative of 60. 5L squared minus 10L. And there we have it. We have the derivative with respect to L. We want to set this equal to 0 and then solve for L. And if we solve for L, well, the 12 doesn't matter because when you times it by 0, so all that matters is the numerator. This is a nice, easy one to solve. 60 equals to 10L, or L is equal to 6. In this case, 6 centimeters. I was going to say, did we actually have centimeters? Let's go back. Yeah, everything was in terms of centimeters. I probably should have labeled the diagram with centimeters. Okay. So we have the length is 6 centimeters. Let's just confirm that that is actually a maximum. So let's just do a quick little second derivative test. So a prime prime of L, well, that's just going to be 60. No, sorry, not 60. You just have 60 minus 10L. Again, the division by 12 doesn't matter. Just like a coefficient, a constant in front. And then it's just negative 10. Or a negative 5 over 6. Always negative. So therefore, if you plug in 6, I mean, there's nothing to plug in. So it's just negative 5 over 6. So L equal to 6 is a maximum. All right, and so let's find out the actual area then. So the area at 6 is equal to 60 times 6 minus 5 times 6 squared, all over 12. And if you go ahead and actually calculate that out, you should get something like 15, and it's an area, so centimeters squared. All right, and let's just go back. Always reread the question, make sure you're answering what's being asked for. We're looking for the area. We found the area. And in this case, there's no n cases because we didn't specify a specific domain. So we don't have to worry about the n cases. So therefore, the maximum area is 15 centimeters squared.